Okay, so the next thing I want to talk about is a general solution to Maxwell's equation. So if you remember, we spoke about a vacuum solution where there were no charges, there was no current density. And now we want to present a general solution that always works, right? So you can always apply this prescription and get the right answer. And the way I want to formulate the problem is as follows. It says that, the type 2 problem. So if I have a rho, a charge density, and J, a current density, how do I solve for the E and B fields using Maxwell's equations? And it turns out that just like in the vacuum case, you don't have an easy way out where, you just take a curl of an equation, you try to get rid of E or B from coupled equations and then get to a solution. It just turns out that once you have charges, rho and J, it's very hard to play some simple tricks and get rid of one of these quantities from the coupled equations, one of E or B from coupled equations. And so you need to do it's harder work. You need to do much more to actually get a general solution. And there's been a lot written about it, and the most general form of the solution goes through intermediate variables which we're going to define, called these potentials. And you can kind of see a parallel between this and what you did with when you studied gravity. When you studied Newtonian gravity, you kind of defined a gravitational potential, right? And so it turns out that all of these, it could be electromagnetic waves, or it could be the theory of gravity. They're all classical field theories, and in all of these classical field theories, the algebra is greatly simplified if you go through these intermediate quantities, which are called potentials. So unlike gravity, where you just had a gravitational potential, when it comes to Maxwell's equations and electromagnetics, you need actually two potentials. And it's basically because you have two vector quantities here. So you can't represent both of them with just a simple scalar, like the gravitational potential. So the minimum you need is one scalar and one vector potential. Okay, so at least one scalar and one vector is easier than dealing with two vectors. So phi is a scalar field. By that I mean phi can vary with space, it can vary with time. It's just a scalar field, and A is a vector field. Okay, so A is basically a vector at every point in space and at every given instant in time. So just like E and B, they are varying with time and they're varying with space. So here's the general solution, and I'm going to go through that, how we get to it, but I just want to state it up front so you kind of know where we are getting, how we are arriving to at a solution using these intermediate quantities. So the first step is actually to go from sources to potentials. So given the sources, what are these potentials? And the second step is, from these potentials, how do I get the fields? So the first step, the solution to the first step, is on the left-hand column here, and it looks like this. You basically get two equations. This is basically a Poisson equation. So one equation is for phi, the scalar potential. The other is for A, the vector potential. And if you see the left-hand form here, it basically looks like a wave equation, right? So second derivative with space, second derivative with time, C being some kind of a measure of speed. So this is just looking like the wave equation, but it's an inhomogeneous wave equation, right? So we do have sources on the right-hand side. This is not zero. If I put zero here, then you get the wave solution, similar to vacuum. And so we have a rho here on the right-hand side. It's an inhomogeneous equation. And again, for A, you again have this kind of a form, which is like a wave, which looks like a wave equation. And I have a current density here. So it nicely separates out. And that's the nice thing, that, there's a different equation for phi, there's a different equation for A. And the whole point here is trying to separate these things out. Once you have a lot of coupled differential equations, it's very hard to solve them. You want to actually separate out. And the easiest way to separate them out is actually to go through this intermediate scalar and vector potentials, and you get two separable equations. Of course, this is the wave equation with a source term, so an inhomogeneous equation, and this is the general solution to the equation. I don't know if you have studied this, but this basically is the Green's function. Okay, so this kind of a function of the form 1 over r is a Green's function to this kind of equation. And so what you get is the solution for phi is rho, which is the rho basically can vary over space. And so this is a three-dimensional volume integral, and r prime is a dummy variable. So you're basically integrating over each point in that volume. You're going through each point r prime in the volume. And your Green's function basically has r minus r prime here in the denominator. So that's just the distance between your position where you want to calculate the potential. So that's the position where you want to eventually calculate the electric and magnetic fields. And that is just the distance between the point where the r prime, where the charges are, and r, where you want to calculate the fields. Again, the same thing for A. Of course, instead of phi, which is a scalar, you have A, which is a vector. Again, the arguments are position and time. All of these quantities are varying as a function of position and time. And instead of the rho, which is the scalar charge density, you have the current density J. So this is a vector equation. Both sides are vectors. And again, very similar Green's function, actually the same Green's function. So that's basically how you get from the charge distribution, rho and J, to the scalar and vector potential. And so what's the second step? That's given in the right-hand column here. The second step is to get to the fields. The magnetic field is just the curl of A, and the electric field is given by the gradient of the scalar potential and the time derivative of the vector potential. So that's the most generic form of solution to Maxwell's equation. All of this also hinges on something called a gauge condition, which I'm going to talk about when I actually go through the formal derivation. You might also have heard of this as gauge fixing. And this is the gauge condition. So you don't have to worry about what the gauge condition is right now. When we go through the derivation, you'll understand what the gauge condition and what gauge fixing are. But this is, just remember that this is called the Lorentz gauge, and we'll be using Lorentz gauge throughout throughout in the course, because it has the nice property that once you want to do a relativistic generalization, things become extremely simple once you assume a Lorentz gauge condition. And for people who have worked with four vectors before, the reason for that is phi and A, when you put together, so one scalar and a three-dimensional vector, they actually form a four vector. And this gauge condition is basically telling you that the four derivative or the four gradient of that four vector is zero. So we'll come to that in later chapters, but it's a nice connection to make, at least to keep in mind. Okay, so let's see, what does the formal solution look like? Well, you basically take B equal to curl of A, the vector potential, and E equal to gradient of phi and time derivative of A, and you just plug them into Maxwell's equations, and you see where you get. So I want to at least, I don't want to just say, oh, just plug this in, but I want to give some motivation here. Why do we have curl of B? Why is B defined as a curl of A? Because we know that divergence of B has to be equal to 0, and divergence of a curl of any vector is 0. So it makes sense to break B into a curl of a vector, because that automatically satisfies Gauss's law for magnetostatics, right? So it automatically gives you divergence of B equal to 0. So you've just satisfied Maxwell's equation just by your formulation, one of Maxwell's equation. So that's written here. So divergence of B is 0. Yeah, that's a vector identity. Divergence of a curl is always 0. That's always satisfied. Okay, so let's get to Faraday's law of induction. Curl of E is minus 1 by C dB by dt. Okay, let's substitute for E. And again, here is the motivation. E is basically, the motivation here is, in some sense, the electric force is kind of similar to gravitational force. The reason for that is the electric force always, if you look at the Lorentz force law, then the force from an electric field is always parallel to the electric field, right? In the same way, the force from a gravitational field is always parallel to the gravitational field itself. And that's unlike the magnetic force. As you saw, the magnetic force is actually perpendicular to the magnetic field itself. So in some sense, this electric field has many properties similar to the gravitational force. And so it kind of makes sense to expand that out as a gradient of a scalar, because that's what you do in gravity. In Newtonian gravity, you just say that the gravitational field is just given by a scalar. You reduce that to a scalar field, and you take the gradient of that, and you can get the forces on particles. But of course, in electromagnetic waves, you can't just stop there, because E and B are coupled. So you'll see that you also need to include this term, and it'll become obvious when we derive why the term is there, and how that contributes. So let's take Faraday's law of induction. Curl of E, I'm just going to substitute for E, because we're just going to get rid of E and B and express everything in terms of phi and A. That's what we're doing here. So curl of that is basically substituting for E, the electric field, and this is basically substituting for the magnetic field. Okay, so let's look at the terms here. So the first term here is curl of a gradient. That's always 0. That's again a vector calculus identity. Curl of a gradient is always 0. And then you have curl of dA by dt. Okay, we can't reduce that. We just keep it as is. On the right hand side, you again have d by dt of curl of A. Okay, so it's basically time derivative under curl. The two operators can be switched because they're linear operators. So LHS equal to RHS. And now you can see why we have added this term here. It's just basically to satisfy this equation, which is Faraday's law. Okay, so now let's take Gauss's law and see where we get it. So we have divergence of E equal to 4 pi of rho. So I'm going to substitute for E equal to 4 pi of rho. And then I basically get divergence of a gradient. That's again the Laplacian operator here, minus 1 over C times the divergence of dA by dt equal to 4 pi rho. Okay, so this doesn't reduce much further. So I'm going to retain this as equation 1 because I'm going to use it later. And so we are done now with 3 Maxwell's equations. We have 1 more to go. And that's Ampere's law. So let's plug all of this into Ampere's law and see what happens. So we have curl of B on the left-hand side. So B is curl of A. So it becomes curl of A on the left-hand side. On the right-hand side, you have the current density. And then dE by dt. Again, I'm going to substitute for E here. Yeah, so again, we are going to use a vector identity here. Curl of curl turns out to be this. So it just turns out to be gradient of the divergence minus, again, this second order Laplacian operator of A. Again, 4 pi by C J remains the same. Here we have time derivative of the gradient and second time derivative of A here. And again, this doesn't reduce any further, right? So I'm just going to call that equation 2. So what are these equations 1 and 2? So we have left with 2 equations here. Everything, the other 2 have been satisfied. These 2 are again coupled equations. So the equations both have A derivatives with A and phi in them. And that's annoying because we went through this process because E and B had this coupled equation. So we wanted to get rid of that coupling and have simpler equations. But we've ended up with a coupled equation again, which is annoying. So this is where gauge condition comes in, and gauge condition is basically one of its virtues is to get rid of this coupled equation, to get a separate equation for phi, to get a separate equation for A. But before we go into that, I need to take a segue and explain to you why we even have the choice of a gauge condition. And so I want to explain that first. So here's a small segue. Just remember equation 1 and 2 are going to come back later. Okay, so if we look at how we defined the potentials, we had B is equal to curl of A. And now let's say that I have a field B and I have a vector field A, and they satisfy this condition. Now suppose I modify A to A prime, where I say A prime is nothing but A plus the gradient of some scalar. Okay, it doesn't matter. Psi is a scalar field. It doesn't matter what it is. And I'm just going to add the gradient of a scalar field to A. So let's see what happens. I take curl of A. I get curl of A plus gradient of psi. Curl of A comes out, and then curl of a gradient is always 0, right? That means that curl of A prime is equal to curl of A, which means B prime equal to B. So B doesn't change. Right, so I can always add a gradient of any scalar field to A, and the magnetic field doesn't change. Okay, what about the electric field? So I have the electric field here, and I'm going to now again, uh, find the electric field, the primed field, where I've made this substitution, where I've taken A prime equal to A plus the gradient of some scalar field. And so you can expand that out. So you can see that this is the old electric field we had, minus 1 over C dA by dt. Okay. So that means that for the electric field to also remain the same, I have to make the following transformation. I have to say phi, the scalar field, the new scalar field, sorry, there should be a prime here, should be the old scalar field plus 1 over C d psi by dt. Okay, so psi is that the scalar field which we added. So here are the possibilities, and this is what is called the gauge. I can always take the vector potential, add gradient of a scalar field to it, and I can take the scalar potential and add the time derivative of the scalar field to it. And whenever I make this transformation, the E and the B fields do not change. That means that I can choose any psi I want, which makes my problem convenient. Okay, and what is the convenience we want here? We want to get rid of that coupled nature of the equations. And so choice of psi is what is called choosing the gauge. Okay, that is what is called gauge fixing, is how you want to choose this psi. And remember, you have any choice you want. You have one scalar constraint to play with. You can choose any psi you want. And so the gauge we are going to use is called the Lorentz gauge. And the Lorentz gauge is expressed as follows. So remember, we have one scalar field to choose. We can arbitrarily have a scalar field constraint. And this is the Lorentz gauge. The Lorentz gauge says that I'm going to choose psi such that this equation is satisfied. Okay, this is a scalar equation. Divergence of A is a scalar, d phi by dt is a scalar. And so I'm going to choose psi such that this scalar equation is satisfied. And you can always make that choice because you're basically satisfying one scalar constraint, which you have to play with. Okay. And so you can, again, I want you to work through all of this by yourself. But the general idea is the equation 1 and equation 2 separate out really beautifully. So here's equation 1. We're going to bring that back. And again, you have dA by dt here, and we want to get rid of this A here. So we have an equation only with phi. So again, get rid of that using this gauge condition, Lorentz gauge. So I substitute for A here. And what ends up happening is you basically get the inhomogeneous wave equation, which I showed you before. Again, here's equation 2, and here I want to get rid of phi, right? So I want everything only in terms of A. And this, you can substitute for phi from this equation, but the simpler way to do it is to recognize that in equation 2 you have gradient of A here and d by dt of phi here, and that's the sum of that is basically 0. So these two terms are going to vanish once you put them together. So again, I'll leave you to actually go through the algebra to make sure that this is right. But here's equation 2 now, and again, that's the vector inhomogeneous wave equation. So basically, choice of Lorentz gauge brought us to a situation where we ended up from Maxwell's equations, which had these coupled equations with E and B coupled, the electric and magnetic field. But now we have reduced that problem into first solving for the scalar and vector potentials, and they are now not coupled equations thanks to the Lorentz gauge condition. And once and there again, they're just solutions to the inhomogeneous wave equation. And yeah, so that's the final solution. This is the solution to the inhomogeneous wave equations. If I give you rho, I give you J, and I ask you what are the electric and magnetic fields, you have a general prescription that always works. You know how to go through that. You use the solution to the inhomogeneous wave equations to get phi and A, and then B is curl of A, and E is gradient of phi minus 1 by C dA by dt. So that's the general solution to Maxwell's equation. This is a general prescription that always works. Of course, depending on the problem, maybe you don't need to go through all of this, but this is basically a general prescription that always works to basically get to the electric and magnetic fields given the charge and current density.